Good morning, good afternoon, or good evening, as always, wherever you are located in the world. And thank you so much for joining us for this month's Amatec Solid State Controls webinar. It is the 20th of September, 2023. And I can't thank you enough for joining this. I know you have busy lives, and I really do appreciate you joining us for this technical webinar today. And today's discussion is going to be on DC ground faults. So as always, to start off with, if everybody or somebody can let me know that you can hear me loud and clear, because there's no point in me speaking to myself or for the next hour. So if you can go to the chat bar on the right hand side and just type in there that you can hear me, then that would be appreciated. I'll wait until I get some replies before I talk anymore. There we go. Thank you, everybody. Good that you can hear me loud and clear. Okay, so just some introductions to start off with. First of all, my name is Craig Williams. I'm the Senior Technical Manager for Amatec Solid State Controls, and I am located in the Stafford office, which is on the southwest side of Houston in Texas. Can't you tell from my accent? My Texan accent. I have 20 years in the industrial UPS industry. It's actually more than that now. I think I started in 2001, so 22 years now. And I've worked with all the major UPS charger manufacturers, and I pretty much would call myself a subject matter expert on industrial UPS systems. Some details about the webinar: there will be a lag of around 15 to 30 seconds between me speaking and you hearing my voice. So therefore, if I'm talking, you're not going to hear it till 15 seconds after I say it. So if there is a question on the subject that I am discussing and you type it in the chat bar, in the chat bar, there is going to be a delay. So please bear that in mind. And for that reason, I usually always wait until completely at the end of the webinar to answer any questions. And if you do have questions, it's much better if you put them in the Q&A section rather than the chat. So if you go to the right-hand side of a chat bar, you can see there's highlighted in blue, there will be the chat function. And then to the right of that, there's a question mark and it says Q&A only. So if you have questions, please put them in the Q&A section if possible. The platform that we use for the webinar is called Webinar Jam, and it does have a panic button. So if I see some comments saying that you can't hear me anymore, or there's some technical difficulties from a lot of people, then I can press the panic button. And what that does is it creates a brand new webinar room, and we get migrated over to that room, and we just carry on from where we left off. So another very popular question is, will the webinar be recorded? And the answer to that question is yes. Obviously, if you're watching this webinar, you registered for the webinar. And if you registered for the webinar, you will get a link once it's complete to rewatch the webinar. Webinar Jam does record the video. But the problem with that webinar is it kind of treats it as a brand new webinar. You press play, and it starts from the start, and you can't fast forward or rewind. So you can't skip things very easily at all. So what our wonderful marketing department do is they download that video, convert it to an MP4, and then re-upload it to the Amatec Solid State Controls website, to our YouTube site, and you can find all of the webinars that we've ever done. And thank you, London. She's just posted it in the chat bar there. There is the link to all of our YouTube videos on our webinars. Okay, so it usually takes 24 hours for them to do that. So it will be available tomorrow at the latest. And it's just a normal YouTube video. You can fast forward, rewind it, pause. You can share it with people. You can do whatever you want with it. There are no restrictions. So we do recommend that you share it if you find that the information is good. And the last thing is, the webinar should last around about 1 hour. And as you can see, I don't know why. I like talking and I do go down rabbit holes sometimes. So I do try and keep the webinar within an hour because I know you have very busy lives. But sometimes it does go over. We'll see how it goes today. And it also depends on how many questions we get at the end. Okay. So I'm just taking a drink of water. So hopefully today, the objectives will go over DC system basics. What is a DC ground fault? How do we detect ground faults? How do you find where that ground fault is located? And also misconceptions around ground faults. Now remember, what we're discussing today only applies to DC ground faults, does not apply to AC ground faults. That's a different beast altogether, and I have neither the skill or expertise to talk to AC ground fault detection systems, only DC. So first of all, we have to start with the system basics. As you can see on the screen here, this is truthfully how we think the best DC systems are designed. So you have your MCC that feeds AC into a charger or rectifier. So it's usually a 480 volt three-phase supply in the US, 415 volts in Europe. And that goes into the AC input of a rectifier. And then that rectifier changes the AC into DC. And then that DC should go to a DC panel, which then feeds the load circuits, and that should also be where your battery is connected. This arrangement here is much easier to maintain. It allows you to take the battery out of service if absolutely necessary, add a temporary battery into the system if you want without losing any of your loads. It's just very versatile. So this is the best designed DC systems as far as we're concerned anyway. So that is the basics of a DC system. So you can see there's the charger there, there's your load circuits there, and there's your battery connected there. And they all have isolation points. There's an isolation point there, an isolation point there, and there's a DC battery breaker there. Okay. Now notice on most industrial systems, inside their rectifier charger systems, there is an isolation transformer. And that is very, very important. And on the next few screens, we'll explain why. And actually what I want to do is let me make this whiteboard here, because I want to start at the basics. Okay, so let's say we have a basic circuit. Let's say this is an outlet in your house. Okay, so we've got line and neutral. Okay, now hopefully everybody on this webinar will know the basics of electricity. And to create a circuit, you would have to have some form of resistance connected to the live and neutral or the hot and neutral to create a circuit and allow current to flow. Okay, hopefully that makes sense. Actually, let me just clear this and draw it again. It's easier. Oh, pencil. So here is our socket again. We have live and we have neutral. Okay, and usually from that socket, you're going to have a ground as well, a ground connection there. So there are a few things that I'm going to say in this webinar that I want to make absolutely clear that I don't want you to do. It's just to show you that what I'm saying is correct. Don't go out and do it in the field, because obviously I can't check to make sure that there isn't some kind of grounding on the system and that you could hurt yourself. But in truth, if you could in some way as a person, so let's draw this wonderful person here, okay? If this person here could touch this hot wire here, and if his feet are connected to ground, and because at the back at the main transformer or the main feed into the system, neutral and ground are connected together, that would give that person an electric shock. Sad face. Okay, so if you are connected to ground and you touch the hot wire, you will get an electric shock. Okay, but if you had the powers of levitation, okay, and this person here decided to touch the live, oh, let me just draw the ground connection here. Okay, but he's levitating somehow, he is not touching the ground, then there isn't a complete circuit. So he would be absolutely fine to touch that cable there. There would be no path through his body for current to flow, and he would not get electrocuted. Okay, if he is levitating and not touching a ground surface anywhere else. Okay, hopefully that makes the basics clear. So therefore, when we introduce a transformer that has isolation, galvanic isolation, in other words, this winding here has no physical connection to this winding here, none whatsoever. There is a insulated gap between those 2 points. They are not electrically connected. As we've just mentioned in that previous slide, the neutral is usually always connected to ground from the main transformer, whether it's in a house or whether it's in an MCC in a plant. But if you put a transformer that has isolation in there, then the secondary of that transformer has no connection to ground whatsoever. None. So once again, in this circumstance here, do not go out and try this, because once again, I can't do any testing to make sure everything is safe. But in theory, a person could come along and they could touch that wire there, and they could be standing on ground, and they would not get an electric shock. And the next slide will show it a little bit better. The next few slides, should I say. So if we use a fluke and we go between live and neutral or live and ground, we're going to get 120 volts AC if it is an outlet in your house. Okay, because that's what we use in North America, 120 volts AC, because neutral is at the same potential as ground. But on the secondary side of this transformer, yes, you will get 120 volts between hot and neutral, or live and neutral, however you want to call it. But because there is no connection to ground, if you go between the hot cable to ground, there should be no voltage. Okay, because there is no reference. But unfortunately, there can be stray capacitances in especially in plants where cable trays hold numerous cables, and you can get stray capacitance, inductance. You can get a ghost potential on there theoretically. But if you put any kind of light load between that cable and ground, it will dissipate. Okay, but in truth, there is no potential between the hot and the ground, and that is exactly the same for the neutral and ground. Okay, there's going to be no potential. I'm trying to drive this in so you understand the importance of the isolation transformer. So you can see here on this slide here, if you connected a lamp between the hot or the live and directly to a ground surface when it's fed from a transformer or the MCC, that will light. Okay, you do have a path because you have this return path back to neutral. It's not the design path, but it is a return path. Okay, hopefully you understand that. But if we connect a lamp or light bulb between the hot on the secondary side of the transformer directly to a ground connection, there is no return path for that electricity to flow. So the lamp will not light. It's impossible. It cannot light because there is no return path to that ground circuit because of the isolation between the two windings. And that's exactly the same for the neutral. Let me go back here. If you connected the lamp to the neutral and down to ground, the lamp would not light. There is no electricity flowing. I'm going to take a drink while that sinks in. Okay. So let's take it one step further now. That was just talking about the isolation transformer. So now we're going to add a rectifier or a charger to the system. So this is exactly the same as what we had on the previous page. Remember, we now have no connection to ground in this system whatsoever. So when we convert that AC to DC, there isn't something magic in the AC to DC conversion that gives it some form of ground anywhere. That's just not possible. It just goes through either diodes or SCRs and converts the AC into DC. So therefore, the positive of the output, which is connected to a battery, and the negative of the output of the system, which is connected to a battery, have no reference to ground. None. In its most basic form, that is how a charger operates. Now we're going to get into the next, as we go down through these slides, that we do introduce a path to ground or a connection to ground so we can detect ground faults, and we'll just discuss how that's done in a little bit. But, you know, what you've got to understand is, yes, these batteries here may be, and actually will be, mounted on a rack. And that rack will be metal, usually metal that's been covered in some kind of insulation, whether plastic, rubber, whatever it is, to prevent a actual connection to the ground. But the batteries will be mounted on a battery rack, and that battery rack, the metal of that rack, will be connected to ground. But the battery positive and the battery negative itself has no connection to ground whatsoever inside a properly designed industrial charger rectifier that has an isolation transformer. Okay. And on this point, this isn't part of the discussion of today's webinar, but just for your knowledge, if you got rid of this transformer, okay, and therefore this point here is connected to that point there, and that point there is connected to ground, now we have introduced a connection to ground, and there will be a potential between the positive to ground and the negative to ground if you don't have an isolation transformer. And therefore, if an electrician does touch the positive post on a battery that doesn't have an isolation transformer in the charger, it's not a DC electric shock you're going to be getting. It's actually an AC electric shock that you'll be getting, because it's AC connected through the diodes and SCRs. And on a 480 volt system, the peak of that can be about 600 volts. So if you don't have an isolation transformer, you're putting your battery technicians in danger if the battery is not disconnected from the system when you're doing maintenance on it. So that is why we have floating battery systems, is to make it safe for technicians to work on without having to isolate the battery. Okay. And just to reiterate, if we took a fluke and we went between the positive of the battery down to ground on DC voltage, there should be no reference whatsoever. There can be stray capacitance and other things giving a ghost potential, as I said with the transformer, but in a very basic rudimentary system that does not have ground fault detection on it, but does have an isolation transformer, there should be absolutely no reference between positive to ground or negative to ground. Okay? Therefore, if a technician accidentally touches the positive post with his bare hands and somehow leans against the battery rack with his other bare hand, no electricity can flow because there is no reference, and therefore he will not, or he or she will not get an electric shock. That is the purpose of this isolation transformer. That is why industrial systems are designed like this, so you can work on the battery safely. So, what is a DC ground fault? Well, the most common cause of ground faults is worn insulation, conductive dust, water, or other soft grounds. Okay? So, obviously, insulation breakdown. So, insulation is the plastic or rubber that is containing the conductors in the system. So, obviously, you can see the copper here, the copper here, and the copper here. So, this insulation has broken down, and these strands of copper wire that are supposed to be going to the load circuits can actually now touch a metallic object outside, whether it's a cable tray or something that it's mounted to, and can touch ground. Okay, that is the first way that we can have a ground fault, is through insulation breakdown. Another way we can do it is conductive dust. This is an actual picture. I'm guessing it's from a sawmill or a paper mill or something. I'm pretty sure they haven't been in this breaker for quite a while. You can see, obviously, there's a huge amount of dust in this bottom left-hand corner, but more importantly, there is a huge amount of dust across these three conductors here. And if that dust is conductive, it is definitely going to cause a short or a ground fault or something bad. I just thought this photo was a very good representation of how dust can cause faults. Another one is water. This is an external junction box. It's supposed to be sealed. Obviously, this is supposed to be a gasket of some sort. This is a junction box. It could be, it doesn't have to be a junction box. It could be an analyzer box, anything that is supposed to be outside and sealed from the weather. But if it has a leak or hasn't been screwed down correctly, it can allow water to get in there. And you can see this isn't resin that's in here. This is actually water inside there, and that's going to short out these two cables. And if this was a metal case, it would take one of those conductors down to ground. Okay, this is actually a very common ground fault path in refineries and petrochemical plants, because a lot of junction boxes, analyzers and stuff is mounted outside in the weather, and you tend to find that most ground faults appear magically when there's a thunderstorm and things get soaked, and that causes one of the polarities to go down to ground. And snakes. It is a funny picture, but it is, we have had situations where possums, rats, mice, snakes, whatever, obviously in the southern states of the US, you do get a lot of critters in your switch rooms because it's a nice temperate climate for them. So you can have a situation where an animal can give you a ground fault between one of the poles and ground. But I just thought that was a very interesting picture. So what is a DC ground fault? Well, a DC ground fault is when there is some form of connection between one of the poles of the DC. So in this circumstance, it is the positive of the battery has a path down to ground. That is the most common not most common. That is the definition of a ground fault. Now, we don't know at this moment in time what the resistance of that fault is, but even if it's a high resistance, it is a connection between a pole down to ground that is not supposed to be there. That's why it says a DC ground fault. And it's important to clarify that, because some people, especially offshore, they will connect their negative to ground on purpose. Okay. So that is a purpose. I don't know what the word I'm looking for is. That is designed to have a negative ground. But this is a fault. This one here. We have a floating system, and somehow the positive has come connected to ground. Okay. Now, if you had a hard ground, there's two terms that I hear a lot. There's a hard ground and there's a soft ground. So a hard ground is when that connection to ground is very low resistance. The fault has very minimal resistance. It's like a dead short from positive to ground. Okay. So if you took your fluke and you measured between positive and ground, you should see 0 volts. Because there is no potential anymore between positive and ground. They're at the same point. Okay? Now, bear in mind, this is not detrimental to the system operation. If you get one ground fault on an isolated, that has an isolation transformer, if you get one ground fault, it's not a problem. That's the design of the system. It's only if you got a second ground fault that it would cause a problem. But you should get an alarm when you get one fault, so you can clear it before the other fault becomes apparent and causes issues. So with a positive ground fault, if you measure between positive and ground on a hard ground fault, you should get 0 volts. And if you go between negative and ground on your fluke, you should see the full system DC voltage, which for most systems that we design is for a 60 cell VRLA battery. It's going to be about 135 volts DC. Okay. If you had a soft ground, which is there is some resistance, usually in the kiloohms, then things get kind of fuzzy. In this circumstance here, you can see that there is the connection is now between the negative and ground, and there is some resistance in there. So when we measure from negative to ground, we are actually getting a voltage 13, 15 volts. There is some voltage between the two because it's not a hard short. And then if you went between positive and ground, when you have a soft negative ground fault, you're going to get about 120 volts. The other proportion of that full voltage to ground. Okay, that's a soft ground fault. Soft ground faults are harder to locate than hard ground faults, but there is a tool that can help you with that, which we'll get to later. So I know through this presentation, there's been so many people shouting at the screen that when I measure positive to ground or negative to ground on my system, it doesn't show me 135 volts and 0 volts. It shows me 65 volts and 65 volts. And you are correct, because that is because somebody has added ground fault detection to either your DC bus or to your charger. And to monitor ground fault detection, you have to give the alarm circuit a reference to ground. And in doing that, what we do is basically it splits the bus in half. And the most basic form of ground fault detection is 2 lamps connected in series with the center point of the lamps connected to ground. Okay? This is the most basic form of ground fault detection. Okay? Now, these are 120 volt, 5 watt lamps. We're saying approximately 3 kiloohms. Okay? Now, what's going to happen, and I'll explain it on the next screen, is the full system voltage is 135 volts DC. Okay, now by putting 2 lamps in series and connecting it to ground, we're actually going to get about 67.5 volts there, 67.5 volts there. Okay, now because this is a 120 volt lamp, that means these lamps are only going to be half lit, dimly lit. Okay, but both lamps should be lit the same, because the amount of current flowing through both lamps should be the same, because we have no current flowing to ground. And then if, oh, sorry, I'm getting ahead of myself. So this just explains, well, what I drew on the previous one. Whenever you have 2 resistors in series that are the same value, it creates what's called a potential divider circuit that has a ratio of 50-50. So basically, the same amount of current has to flow through both resistors, so therefore the same amount of voltage will be dropped across both resistors. It's Ohm's law. You cannot change Ohm's law. So if you put 2 lamps of exactly the same resistance in series, you create a potential divider and you will drop half the voltage across both resistors, or lamps in this case. Okay, so yes, the total voltage between positive and negative is 135 volts, but if you divide that by 2, you get 67.5, and that's what you should see between this point here and this point here, and from this point here to this point here. And because we tie this center point down to ground, therefore you now have 67.5 volts between negative and ground, and 67.5 volts between positive and ground. So we have deliberately now created a reference to ground. But because these are high resistance resistors, it doesn't allow much current to flow between positive and ground and negative to ground. So we can control the current, and therefore somebody is still not going to get an electric shock if they touch the battery terminal, because there's only a minimal amount of current that can flow. Okay, so why use 2 lamps? Very easy, because if you have a direct short between positive and ground, let's say the insulation on this positive wire has failed and is touching the cable tray, which is grounded, then now we have a direct connection between positive and ground. Well, now you're going to have 0 volts DC across this lamp, and that lamp is not going to light anymore. It needs potential to light. But if you go between negative and ground, because this point here is now at 135 volts potential, this lamp is going to go very bright. And that's what indicates that you have a positive ground fault on the system. Okay? Hopefully that makes sense. And the exact same happens the other way. If you have a direct short between negative and ground, if you go between negative and ground with your fluke, you're going to get 0 volts DC. If you go between positive and ground with your fluke now, you're going to get 135 volts DC, and this lamp will go bright and this lamp will go off. So that is the most basic form of ground fault detection, and that is why you get the ground on your DC system is going to be roughly halfway between the positive and negative. So in truth, that's how we used to do things. Obviously, technology advances. There's better ways to do it. There's better ways to increase the resistance between positive and negative to the ground conductor to prevent anybody getting an electric shock from this circuit being installed. And the way to do that now is using an alarm board or an alarm configuration of some design, where they have a resistor here and a resistor here, which is a very high value. It could be 10K. It's going to be a high value. And then that goes into an op-amp circuit, which basically uses a ground as a reference, and it will monitor whether these points here are where they should be away from ground. And if one of them tends to go towards ground, then you'll get an alarm signal out, and it will either show you on a display. It could be a lamp. It could be it could go to your DCS system. But we don't use lamps anymore. We use a more complex alarm board circuit. Most manufacturers do these days. Okay, there are still a lot of systems out there that are old and have the lamps on the front, but most of our systems now use alarm boards. Okay, and I'm not going to go into this design of system, but there is a DC ground fault detector called a bender, and it does not use resistance, a potential divider resistance circuit to monitor grounds. It actually injects, I think it injects a signal between positive ground and negative ground, and then it detects if that signal comes back the way it should do. And this bender does not create that potential division between positive and ground and negative and ground. You won't, if you have a bender system on a DC system, it will not have the 67.5 volts to ground from positive or 67.5 volts to ground from negative. It does something completely different. So bear that in mind. And I don't have time, nor do I have the knowledge on what these bender systems do. I used to, but it's been a long time since I've used them. So that's where we are with that. So bear in mind, if you do have a bender system on your DC system, you're not going to measure, let's say, ground there. You're not going to measure the halfway point between positive and ground and negative and ground. Okay, so let's find the fault. Once again, back to our typical DC system. And we have a positive ground fault alarm on the charger. Okay. So what do we do? Well, the first thing that we need to do is find out where the fault is. Is it in the charger, for example? What we want to do is break it down into sections and figure out where the fault can be. And we should be able to do that without dropping any of your loads, unless the ground fault is on one of your load circuits. And I'll explain that in just a moment. So if we suspect that the ground fault is in the charger rectifier system, the first thing that you should do is open the DC output breaker on the rectifier charger. Okay, so basically what we're doing is we are disconnecting the charger from the DC panel and the battery. The battery will maintain your loads, so you're only going to do it for a short period of time. Make sure your battery is available and it is capable of providing the load. But what you can do is open this breaker, and if the ground fault stays on, if the ground fault alarm stays on, then yes, something inside the charger has gone to ground. That is extremely unlikely. It's very, very unusual that the ground fault is actually in the charger. Unless maintenance has been performed on that charger, somebody has replaced the DC capacitors inside this system. So there's a positive and negative. And what I've seen is on DC capacitors, they're aluminum. So the casing of the capacitor is aluminum, so it's conductive, but it is covered in an insulated material. And what you'll find is you get a clamp that looks like this, where a screw goes through here, and there's a mounting bracket there, a mounting bracket there, and a mounting bracket there. And what you're supposed to do is you're supposed to fit the capacitor into this bracket and then tighten this screw to clamp it down. What tends to happen is getting to this screw here can be an absolute pain. So a lot of people, they just try and loosen it as much as they can, and then they'll wiggle the old capacitor out. And then when they put the new capacitor in, they'll wiggle or screw it kind of in. And what that can do is it can cut the insulation on one of the DC capacitors. And if you cut through the insulation and the can of the capacitor touches the clamp here, well, the can of the capacitor is actually connected to the negative terminal of the capacitor. So you will create a ground fault if the insulation on that capacitor has failed. Okay, so that is really the only should ever be I can't speak today. The only time that you will ever see a ground fault in a charger is usually either down to a wiring issue or down to capacitors that have had the insulation broken down because somebody's installed them incorrectly. Okay, now obviously if you do open this DC output breaker and the ground fault clears inside the charger, okay, if it clears, then we know that the ground fault is somewhere out here, okay, because the ground fault in the system is cleared. And that is what's going to happen in the majority of cases. Okay, you're going to open this output breaker and the ground fault will clear. So if the ground fault clears, then what we can do is now we can test the cable between the charger and the DC panel. Hopefully your system has been installed like this. So what we can do is we can close this output breaker back in again, and then we can open this breaker. And if the ground fault stays on, then now we know that the fault is in the cable between the charger and the DC panel. If the fault disappears, we now know that it can only be these load circuits here or this battery. So basically, if we open this breaker here and the ground fault clears on the charger, that means it has to be the load circuits or the battery that have the ground fault. So then the next easy thing to do without dropping the load circuits, hopefully, is with leaving the charger online. Now, you do have to make absolutely sure that your charger rectifier can maintain your load circuits without a battery. I don't know why some people call it a battery eliminator charger. I hate that term because it doesn't eliminate a battery. It just allows the charger to maintain its 135 volts load because it's got a lot of DC capacitors inside it, which filters out the AC content of the output of the charger. Okay, you cannot open a battery breaker on a system, on a DC system that doesn't have any capacitors in the charger, because the actual output of the charger will look like that. It will be pulsating DC, and if some of your loads are sensitive to these dropouts in between when it goes down to 0 volts, then you could cause an issue. So make sure that your rectifier charger does have capacitors inside it before you open the battery breaker. Okay, but what you can do with all of these breakers closed, everything on, if you open the battery breaker and the DC alarm, the DC ground fault clears on your charger, then there is a ground fault on your battery somewhere. Okay, if you open this breaker and the ground fault remains, then we know it's one of these 3 circuits. Absolutely guaranteed. Okay. Now, a lot of people say, well, why would a battery go to ground? Well, remember that I said that the battery is always sitting on a battery rack. What can happen? The 2 things that I've seen happen that create a battery ground fault is either there's a leak in the jar of a wet cell battery where the electrolyte leaks down and somehow gets to the metal of the battery rack. Okay, and then that gives a conductive path between the internal of the battery down to the ground of the battery rack, and that will give you a ground fault alarm. The other thing that I've seen is the cables that go to the battery they're usually tie wrapped very tightly to either cable tray or the battery rack stanchions or something like that. And what can happen is if there's any burrs on the cable tray or on the battery rack and there's any kind of vibration in the system, that can poke through to the insulation eventually and can cause a ground fault on the battery. Okay, they're really the only two ways you can get a ground fault on the battery. Okay. And the last one is in the DC panel. That's the only, so we've said the charger is okay, we've said the battery is okay. It has to be one of these circuits. And unfortunately, at that point there's only that you have two options. You can either isolate each load until the fault goes away, and then you know that it is the load that you isolated that clears the alarm fault that has the problem. Obviously, to do that, you're going to be de-energizing your load circuits, which is never usually a good thing. But if you're in a position where you can do it in the plant, that is by far the easiest way to do it. That's what this screen is saying. But the problem with that is, in most circumstances, you know, this DC panel may be feeding another 4 or 5 loads. So yes, you are, let's say we open this breaker here, the ground fault clears. Well, we know that it's this branch here that has the problem, but unfortunately there's maybe 5, 6, 7 pieces of equipment that's connected to that circuit. Then we have to go and try and find which individual piece of equipment has the problem. So there are issues that you can find with just by opening breakers. Okay, this one here is saying open at circuit 1, open circuit 2, or open circuit 3. Find out which one clears the fault. That's the most unscientific way to do it. The most scientific way to do it is to buy a ground fault detection system. And the most popular one in the US is the Mega BGFT, the Battery Ground Fault Tracer. And this picture on the screen, that shows you exactly what it looks like. And what that does is you connect the signal generator between so first of all, you have to detect whether the system has a positive ground fault or a negative ground fault. So we're saying we have a positive ground fault alarm. So what we then do is connect the signal generator part of the BGFT, the red lead to the positive of the system, and then the other lead to the ground of the system. And then what the signal generator does is it sends a signal only down the path where the ground fault is. So it's sending a high frequency, low current signal down the fault path. And then what you can do is you can take the receiver side of the Mega, which is tuned to the exact frequency that the signal generator is sending, and you can use an amp clamp style receiver and put that amp clamp receiver around this circuit here. And the BGFT will tell you if there is a signal there or not. If there is no signal, then that does not have the ground fault. It's only when you say, so let's say signal, don't see a signal on circuit 1, that is good. Circuit 2, no signal, that is good. You see a signal on circuit 3, that means that is where the ground fault is, because it's going down here and back to ground. And therefore you know that circuit 3 is the issue. And then if you have a sub panel fed here, what you can do is you can take that amp clamp receiver and you can go on each of the sub loads and find out which individual one still has the signal. And then that will tell you where the ground fault is. This is an excellent piece of equipment. It's quite expensive, but if you do get frequent DC ground faults at your system, it is very easy to set up and find those ground faults without having to disconnect any of your loads and without jeopardizing any of your loads. Okay. And these pictures just showing you moving the amp clamp to the different positions. Okay, so common misconceptions. The alarm is on the charger, so the fault is on the charger. Well, I think I've discussed that. That is the most common misconception we get, because the red alarm comes on the charger and it says DC ground fault. Everybody says, well, it's on the charger, so the fault must be in the charger. That it's so rare that is the case. It's usually always downstream of the charger out here. Such a common misconception. This is just the alarm circuitry. The actual fault is going to be out here. 99 out of 100 times. I can't give you 100% on that. Sorry. The next misconception is when I measure between ground and the battery, I get weird readings and they move. Okay. Well, remember, if we go back to the start, if we have a true isolation transformer and we have a charger that does not have any kind of, I'm drawing that terrible, that does not have any kind of ground detection system on it, then we don't know what the voltage between positive and ground is and negative and ground is. And when you put your fluke between positive and ground and negative and ground, yes, your fluke is a high resistance piece of equipment, but it does have resistance. So it is going to tend to pull that down to 0 volts. So let's say you measure it at 35 volts to start off with, there's some kind of stray voltage in there. It will start to tend down towards 0 volts. That's not an issue as long as the system doesn't have ground fault detection in it. If you're getting weird readings and you have ground fault detection, then you have to do further investigating. Okay. But if you don't have ground fault detection in your system and you go between positive and ground and negative and ground and you get weird readings, then that is normal. Absolutely normal. And I think this is the last misconception. I don't have to worry about ground faults. The system will still work okay. And in truth, that is a true statement, because that's why we have, one of the reasons we have a floating system is if we do have a ground fault, then the system will still work without any issues in most cases. Okay, there are some exceptions. So this circuit diagram here is a trip and close circuit on an MCC. Okay, here's our trip coil, and there's trip signal, and there's other auxiliary contacts doing other stuff. Okay, and here's our battery on the left-hand side, which is actually going to be connected to a charger as well. Okay, so if we have a fault between the DC bus and ground, we're still going to have our 135 volts available for all of this circuitry here to work. That's not going to be affected. Everything is still going to work fine. And actually what you see here is this is a really old-fashioned tripling and closing circuit, and each circuit has its own ground fault detection on it. They've got their own potential divider here using a lamp. Okay, that's all these resistors are doing. So if you get one fault on the system, not a problem. All it means is now the positive bus is now referenced to ground. No high current is going to flow. Nothing's going to break. Usually it's all fine. It's only then when you get a second ground fault on the negative bus that we have issues. Because now you can see we have a direct short between that fault there and this fault down here. And as you can see here, we have two fuses. And if we have a short, there's going to be high current flowing. These fuses will blow, and that will prevent the tripping coil from energizing. So the breaker will probably trip instantaneously and cause you all kinds of problems. Okay. So one ground fault isn't a problem. It's only when you get a second ground fault that you do have a problem. And wow, I finished 5 minutes before the end of the 1 hour, which is impressive for me. Okay, so let's see if anybody has put any questions. Yes, they have. So let's have a look. Let me go down to the start. Bear with me, guys. So the first question, are battery racks always grounded? 99 times out of 100, yes, your electric code should say that your battery rack is grounded. I can't really think of any reason why your battery rack isn't grounded unless it's made of a material other than metal, completely, that it has no metal in it whatsoever. I've seen some fiberglass racks that are quite sturdy, but if the rack has any metal content in it whatsoever, it should be grounded as part of your electric code. Somebody's asked if a PDF version of the presentation can be sent out to participants. Unfortunately, it is proprietary, so we do not send out PDFs, but you can share this video as much as you want. You don't get a PDF version, but the video will be available on our YouTube channel after you have viewed it. So yes, no PDF, but you can share the video. Okay, somebody's asked, didn't we say earlier that if tech touches the positive post and the ground of the battery cabinet, that would be okay? Yes, absolutely. In a system that is working correctly, if a battery technician touches an industrial battery charger system connected to an industrial battery that is on an insulated rack that is not connected to ground, and he touches any terminal on that battery and touches a ground connection, he will not get an electric shock. Basically, all that will happen is he or she has then referenced that pole of the battery to ground. No current will flow. He or she will be perfectly safe. Now, remember, I'm saying that from a system that is maintained well and is working correctly and has no other ground faults or paths in it whatsoever. I've done it. I've shown it to many of my students. I usually do it with a light bulb, so I don't put myself in danger. But if the light bulb doesn't light, then no current is flowing and you are good. Do you have any recommendations on how to determine the alarm settings in a DC ground relay? Unfortunately, I don't go into we look at this more from a charger UPS manufacturer rather than a relay manufacturer for switchboards and DC switchgear. I think the industry standard always used to be, let me get my figures right. I think it was 30 milliamps, because they decided that 30 milliamps was the cutoff for the power required for a relay coil to energize accidentally. So I think anywhere between 30 and 60 milliamps, depending on the voltage of the battery, used to be the industry standard for the settings for milliamps on a DC ground fault. But that's more of an engineering question that you would have to ask your engineers if they have a specification for what they should be set at. Because once again, remember, I don't know what the voltage of your battery is going to be. So it could be, it's all based upon the voltage of the battery, the resistance of the fault, and that derives the current available to energize a coil. Do we get any certificates for watching this webinar? Unfortunately, we don't issue any, is it the P certificates or anything like that? And because we have to go through some form of checks and balances to do that, and I'll be honest with you, we haven't done that. So there are no certificates. You can get a certificate that you attended the course, I think, or you can get an email saying that you attended the course, but you don't get any kind of PE certificate or a certificate to give you credits, CEUs or whatever they're called. We have a question. How do you determine if you have a positive or negative ground fault? Okay. Let me see if I can go back. Actually, you know what? Let's just bring the whiteboard up. It's much easier to do it on the whiteboard. So we have our battery charger here. Oop. Battery charger AC in, DC out. We have our positive here, and we have our negative here. And then we have our ground over here. Okay. Remember, if you have a positive ground fault, okay, then if you measure with a fluke between positive, so you go to your fluke, there's our voltmeter there, and ground, you will see 0 volts. So whichever pole has 0 volts or the least amount of volts is the pole that has the ground. This can sometimes confuse people. Okay, they think the one with the highest voltage is the one with the ground. That's not the case, because remember, if you have a ground fault, you've basically got a short circuit between the ground terminal and the positive terminal, and there will be no potential there. So if you have no potential between positive and ground, then you have a positive ground fault. And vice versa. Let me just draw it once again. Positive, negative, and our ground here. If you go between negative and ground with a voltmeter and you see 0 volts, then you have a negative ground. It is the pole that has 0 potential that is where your ground fault is. Okay, somebody's asking, I said direct fire is seldom the cause of the ground fault, but I explained that it could be a capacitor. I'm terrible at drawing, but I will try my best. So here is a capacitor, okay? Positive terminal, negative terminal. Now, bear in mind, this negative terminal internal to the capacitor is actually connected to the can. Okay, it's actually physically connected on purpose by the manufacturer. Okay, so the can of the capacitor is connected to the negative terminal, but the can is usually covered in plastic. Okay, so when you put this capacitor inside that clamp that goes around here to keep it in place, and it goes around the back there, then there is no way for the can to touch this metal clamp and cause a connection. But what tends to happen is when people try and insert these capacitors into these clamps, they don't loosen the clamp up enough and they have to screw it in. They have to really force it hard in. And what that does is it usually peels a little bit of the insulation at the bottom of the capacitor here. And that's enough for it to touch this clamp. And then when it touches this clamp is connected to the frame of the charger, which is connected to ground. And therefore you have created a path for the negative of the battery, because the negative of the capacitor is connected to the negative of the battery, down to ground. Hopefully that will explain how a capacitor can do that. And also just remember, inside a charger, if there is a conductor that has any insulation showing on it and it touches the frame of the charger, it could cause a ground fault as well. So it's not impossible, it's just very rare. Which portable locators beside the Mega do you recommend for looking AC and DC grounds on big distribution networks? Oh, damn, Jan, great question. I don't have the skills or the knowledge to tell you that. I work on only up to 480 volt systems, and usually within charger and UPS systems. And the only two that I know are the Mega version, and I used to use one in the UK, and I think that system was made in India. I can't even remember what it was called. It came in a leather, an old-fashioned leather pouch. Was it called a Doctor? No, a Grouser. It was called a Grouser. But once again, that was only for DC systems. I can't comment on AC ground faults, unfortunately. Okay. Could I discuss the influence of common mode voltage, PWM from the inverter, on IMDs? Andre, I am unfamiliar with what an IMD is and whether your question has a reference to ground faults, or if you can type in the Q&A and explain the question more, I might be able to help. Another question: does the electrolyte on the battery ground need to be wet to cause a ground? Can it be dry and still be conductive? Very good question, Brooks. Yes, it does need to be wet, but I'll caveat that with, if there is, like, even if it's a glass mat or a gel cell, there could be some liquid electrolyte leaks out from the leak because the jar is not pressurized anymore. And then if that does touch the rack, and corrosion on the rack starts, and that corrosion will give a path to the plates inside the battery eventually. So it's not out with the realms of possibility. It's just much, much more likely to be a fault path with a wet cell, because it's obviously it's liquid. Hopefully that answers your question. Thank you, Andre. Installation monitoring device, and you are absolutely correct. I can't really discuss. So basically, what Andre is asking is, how does PWM on a UPS affect the voltage sensing on an installation monitoring device? And in truth, it's not just PWM. It can be the switching of the rectifier as well. Because the bender and the installation monitoring device that sends a signal to monitor the ground fault relies on the same signal coming back identical to what it is expecting, any other common mode noise that is on that circuit can affect it. I've seen many issues when a bender is used on a UPS system, or a high frequency charger system where the DC is being created by some form of PWM, or there is reflected PWM from the inverter of the system. So I don't recommend using the bender or any kind of any kind of installation monitoring device that sends a signal while the system is in normal operation. I do like the Mega because that's a test device that you use to try and find the fault, and it's not consistently on the system. But the ones that are used on a charger, I just personally, I don't like them. But that, once again, that's personal. I'm sure Bender and all the other manufacturers will have a completely different viewpoint, and will say that they work absolutely fine. Okay, so another question on the capacitors. Based on your explanation of capacitor construction inside a charger, may we say the internal failures to a charger are more common to the negative to ground than positive to ground? In my experience, absolutely. But once again, that is my experience, because, you know, the capacitor manufacturers tend not to have the positive of the can connected to ground. There are other things, like I said, within a charger, it can be insulation wear on a cable, and that can be on either positive or negative. It could be that there is a loose connection, and that loose connection has come apart and is touching the ground, and that could be on positive and negative. But in my experience, in the 20 odd years that I've been working on DC systems, it tends, if it's in the charger, it tends to be a negative ground fault. Okay, let me just go to the chat bar just to make sure nobody's put any questions in the chat bar. There are a few in here. So Damjan, yeah, the Mega BGFT is only for, it's a battery ground fault detector, so it's only for DC systems. Can you go over the isolation transformer slide again briefly about how the AC shock could occur without the isolation transformer? It is important, so I will go over it. I know we're running late, guys, and if you've had to log off, I completely understand. But this is very important, and there are so many commercial style UPSs out there, that especially older ones that don't have isolation transformers in them, that consistently shock battery technicians all the time. I've been shocked by one of them right at the start of my career, and I wondered what the heck happened. And it is down to not having an isolation transformer. So let's go back. Sorry, the way that this program works, I can't select the slide and go back. No. Well, let's just do it on this slide. So you've got to remember that on any system, the electrical code says that the neutral point must be connected to ground at one point and one point only, and it's usually at the earliest point in the system that connects from either a transformer on a pole outside your house or from your MCC. So your MCC will probably have the neutral connected to ground, or the transformer before your MCC will have a neutral connected to ground. So my point is that the neutral will be connected to ground. Okay, so if you remove this transformer here, this point here is connected and this point here is connected. Okay, so for ease, let's say there is now 120 volts between this point here and this point here. And remember, this point here is now connected to ground. Now, there isn't anything magic inside a charger. It's SCRs and diodes. It could just be diodes. So let's say it's a diode bridge. So I'm going to test my bridge drawing capabilities. So that gets connected there, that gets connected there, and then that gets connected down there, and that actually goes over to this point here. Okay, so it's just diodes. So this point here, because this diode is forward biased, it will have 120 volts with respect to ground. Okay, people will say it's DC. Yes, it is, but it's a half a sine wave that has been rectified. So it will, these peaks here will actually be around about 160 volts. Okay. And because you have a connection to ground. When you touch this battery terminal and you touch ground, you will get an electric shock. But it's not a DC electric shock. It's not coming from the battery. It's coming from the path. So the path will be, let me change color. Because this is important. Let's change it. So that color there. So the path is going to be out through here, through this diode, out to the battery, back down through the negative, down through here, back up through this diode here, and down to that ground connection. Okay, so if you touch this point here, you have a path back to ground. So if you touch this point here, as this fault shows here, this is actually a person, and he touches the battery rack. He or she is creating a path to ground where electric can flow, and he or she will get an electric shock depending on how sweaty their hands are, if there's any insulation on the battery rack, how much connection he makes, what the pressure is. So yes, absolutely. If you don't have this transformer, then you will get an electric shock when touching a battery terminal. On the diagram I just drew, there is no voltage between the positive and ground. Can you explain why we feel an electric shock if we actually then touch the positive while standing on the wooden floor in my house on the 120 volt outlet? I would. I don't know the resistance of your wooden floor. Is it insulated? Is it an engineered floor? You know, there is it's basic Ohm's law. Because remember, in your house, this is irrelevant. You don't have an isolation transformer. The neutral is connected to ground. So if you touch this positive point here and somehow you get to the ground in your house, now remember, your concrete in your house or the frame of your house, if there's any metal in it, has to be connected to this ground connector here. So if you do get a shock on your wooden floor, it must mean that your wooden floor is not giving you complete isolation from this ground circuit here. So that is why you would still get an electric shock. Any path to ground whatsoever, if you don't have a transformer, which all houses do not have an isolation transformer, the code says you have to have neutral connected to ground to give a return path to clear any breakers and prevent people from getting electrocuted. So it's got nothing to do with DC ground faults. It's more about personal and fire safety for why we do grounding in buildings. Hopefully that explains what you're asking. Okay, now we're 20 minutes past time. Let me see if there's any more Q&As. From Eric, absolutely yes. It says, in our plant, our chargers run on 480 volts to charge at 130 volts DC. Do those work in the same way as 120 volts that I'm showing with the isolation transformer? Absolutely. I just choose to use 120 volts because people tend to understand it more, because that's what comes out of a house outlet. But they do work identically. It would just be a three-phase transformer, and that three-phase transformer has complete isolation. And the last question is, in that case, do I recommend a particular strategy to monitor insulation in the case of a PWM converter? In truth, Andre, the basic resistance method is by far superior to any bender or any other insulation monitoring. The PWM does not affect having a potential divider across the positive and the negative. And we usually have, if it goes to an op amp on the control board, that usually we'll put it through a buffer or some isolation, and it won't cause an issue. It's just basic, and it's easy, and it's by far, in my opinion, the most robust way to monitor DC ground faults, because it's simple. Okay, I think that is about everything, and I loved everybody's questions. That's fantastic. I know we've gone 20 minutes late, but I love answering everybody's questions. And there've been some very, very good questions today. So at this point, I'd just like to thank everybody for joining us for this webinar. I really do hope that you enjoyed it and you got something out of it. That's what we're looking for. We want you to learn stuff from these webinars. Don't forget that the webinar will be available on our YouTube channel by tomorrow, and you can watch it, share it. It's not locked in any way, shape, or form. You can send it to your friends, do whatever you want. London has put the link in the chat bar. You can also, if you have any questions about anything related to UPS and charger systems from Amatec solid state controls, you can call the number that London has posted in there, 1-800-635-7300, or you can email us or use our website to contact us. The link is there and the email address is there as well. And one last thing, you will get a survey because you registered for the webinar. Please take the time to fill it out, especially I think it's question 6 when we ask what you would like us to discuss at our next webinar. I read every single one of those surveys, and it really helps me tailor the webinars to give you what you want, rather than me just talk about stuff that may be irrelevant to you. So please fill out the survey and let me know what you want me to discuss at next month's webinar. Oh, one final question came in. How do you detect intermittent alarms? My funny answer to that is you bang your head against the wall, because it's nearly impossible. Intermittent alarms are the most difficult things to find. What you have to try and do is narrow it down to when is it happening, and is there anything else that's happening in the plant at the same time that correlates to that fault. And what I mean by that is, does the fault only come in when it's raining? Okay, so if it's only happens when it's raining, then you know that somewhere out in your plant, moisture is getting into something somewhere that is causing a ground fault alarm, and you can do your troubleshooting that way. The best way. That is the only answer I can give you, Ali. Apart from that, it is extremely difficult because and even if it is moisture, what tends to happen is, if it's only a little bit of moisture, the small amount of electric current that flows through that will heat up that moisture and make it evaporate, and it will go away. So yeah, very, very difficult in some circumstances. Okay, that's definitely enough for me. Thank you everybody for joining us for this webinar, and until next month, take care, stay safe, and we'll speak again soon. Thank you.